So it's about time to have today's seminar. And then, since we have quite a lot presented today, in total 5, if I'm not mistaken. So I only open for 2 questions for each presenters. Okay. And then, let's welcome the first presenter, Wang Xiangmi.
Good morning, everyone. My name is Xiangmi Wang, and my advisor is Professor Xiaobin Wang. And today I will present our research that shows temporal NHS distributed routing for dynamic LEO satellite. Here is my outline. I will cover the stage 1 calculation and our main consideration. And I will explain the system model, our POM-TP formulation, and the proposed JPLSTM equivalent architecture. Finally, I will share our simulation results and a green AI analysis. In the 6G era, achieving seamless global connectivity relies on the space-air-ground integrated network. Within this multi-layer framework, LEO satellites act as the critical backbone, providing essential coverage for remote area, disaster recovery, and global IoT. LEO satellites offer 4 major advantages over traditional GEO. Number 1 is low latency due to much shorter propagation distance. Number 2 is low payload for better overall transmission efficiency. Number 3 is global coverage through mega constellations. Number 4 is flexible deployment with faster scaling and lower cost. However, LEO routing faces two unprecedented challenges. First, dynamic topology from extreme satellites. Velocities cause frequent link change. Second, time-varying traffic creates periodic unbalanced data service. Consequently, static routing inevitably leads to severe congestion and packages. To tackle this, we mathematically model the complex 3D orbital dynamics of the 2D logical grid. Each satellite acts as a node maintaining 4 continuous inter-satellite links with its neighbor. Our goal is to dynamically find the optimal routing path within the least shipping grid. Existing deep reinforcement methods like FDR-MAI, DQIR, and GRID-PR all share the critical flows. They rely entirely on instantaneous feedback or purely spatial feature. They fail to capture temporal traffic dynamics, meaning they only react to congestion after it occurs. This massive gap drive our moderation. Conventional networks struggle to process the graph structure nature of LEO GAT and LDN for proactive translation avoidance. Number two is scalable distributed theme. Formulating the routing pattern of the POMGP for doing decentralized decisions. Number three is superior performance. Achieving up to 23% Q reduction compared to all baseline. For our simulation environment, we utilize a local data constellation consisting of 45 LEO satellites. And we define the network as the time-varying graph. KT arrivals follow a non-homogeneous Poisson process with periodic intensity. Q dynamics are strictly modeled. The next state depend on transmit and newly arrived KT. Delay comprehensive include propagation, transmission, and queuing. Because generalized make a global view, we formulate a DO entity. The state use local Q length, delay, and topology. And the action is select the optimal network. And our reward penalize both delay and congestion, forcing the AI to sacrifice a slightly longer path to proactively bypass congestion. First, for special feature extraction, we choose direct attention network or GAT. The topology of an LEO constellation is inherently a non-Euclidean structure network, which conventionally neutral network cannot handle. GAT is uniquely suited for this because its attention mechanism allows each satellite to dynamically assign different weights to its neighbor based on their real-time state, instead of treating all neighbors equally. Our agent focus heavily on nodes that are become concatenated, providing sharp spatial awareness. Second, for temporal density modeling, we employ LST and satellite traffic is highly time-varying, dynamic, and periodic. Existing networks only look at instantaneous network states, making them reactive and short-sighted. LSTM is exceptionally well suited here because it captures long-term history of traffic patterns to predict future congestion trends before they actually happen. This temporal foresight transforms our routine strategy from reactive to proactive. And finally, for distributed policy learning, we implement a DQ network for DQ1. In the massive data constellation, centralized routing is impossible due to severe propagation delay. DQ1 serves as the ultimate decision engine to fuse the special features of GAT and temporal trend from LSTM into a single Gilbert function. Enabling each satellite to independently and instantaneously select the optimal next hub using only local observation. He delivered the perfect overload under heavy traffic. We achieve the lowest daily loop rate and reduce average queue length by 23%. So LSTM successfully allowed the satellite to loop ahead and avoid trouble. We also conduct a green AI analysis. Our joint modeling does include the highest computation time and power consumption among all the baseline. However, the absolute energy cost is extremely low. To put this into perspective, it is equivalent to powering a standard 10-watt LED light bulb for just 81 seconds. In conclusion, we propose a fully distributed GATRCM deployment framework for proactive congestion avoidance. And number two is we significantly outperform baseline, reduce queue length by 23%. Number three is we prove our system is practically scalable and aligned perfectly with green AI principles. And this is my reference. And thank you all very much.
Sorry. Continue.
I'm not open to any question.
Okay, thank you. So we open for two questions.
Why did you choose a pure MDP formulation instead of a standard MDP for your routing problem?
Thank you for the question. We formulate the routing problem as a pure MDP because global network information is not fully observable by an individual satellite due to high propagation delay and the massive scale of LEO constellation. In our framework, each satellite operates as a decentralized agent that must make immediate desktop decisions based strictly on local observation, such as its own queue length, neighboring delay, and local topology feature. Standard NTP would unrealistically assume that every satellite has real-time knowledge of the entire network traffic, which is practically impossible in a highly dynamic satellite network.
How exactly does the combination of DAT and LSTM enable proactive congestion avoidance rather than reactive routing?
Thanks for the question. The combination enables proactive routing by jointly capture couple spatial and temporal dynamics. Spatial DAT module extract spatial feature by an dynamic modeling of long Euclidean structures, assign higher attention weights to neighboring nodes that are expanding in queue size, and the spatial representation are fed into the LSTM module, which learn historical SQL data to predict future trends and periodic congestion patterns right by the NHPD arrival process. This temporal provide a lower equivalent decision engine to locate around potential bottlenecks before buffer overflow actually occur rather than merely reacting to instantaneous wireless system. First, let us look at the previous work. This design shows a bidirectional KA band front-end module with very compact implementation. The main idea is folded passive RF component for multiple functions. The advantage is high integration and small chip area. However, this kind of design usually needs complicated passive network design, which makes optimization more difficult. The second work uses a switchless bidirectional amplifier. Its main advantage is removing the traditional transmit and receive switch. This helps reduce insertion loss, which is very important in high-frequency circuits. However, this type of architecture usually have limited flexibility. So, from previous works, we can summarize several advantages. First, they reduce chip area. Second, they improve integration. Third, they avoid extra switch loss. But there are also limitations. Number one, gain control flexibility is often limited because many bidirectional architectures strongly rely on shared signal path. Once the transmit and receive functions are tightly coupled, adding independent gain tuning becomes more difficult. Number two, compact integration improves area efficiency, but it often introduces extra passive loss, routing constraint, and performance compromise between transmit and receive requirements. Number three, although these architectures are highly integrated, the circuit design becomes more complicated because multiple functions are strongly coupled together. So the optimization of one performance metrics may unintentionally degrade another. So based on this observation, our motivation is clear. First, extreme bidirectional architecture often rely on complicated shared matching network, which increase design difficulty and reduce flexibility. Therefore, one of our goals is to achieve bidirectional operation with a more structural and scalable architecture. Second, we want to improve PA efficiency under 6 dB power backup operation. This is important because real wireless systems do not always transmit at maximum power. Third, we want dynamic high power and low power transmit operation. Finally, we want to integrate PA and LNA into one compact architecture. Now, let us move to the proposed architecture. The system includes 3 main blocks: a 2 WDP-based switching network, a dual-mode power amplifier, and a current reuse low-noise amplifier. The key idea is using reconfigurable 3-way Wilkinson power divider. Traditionally, Wilkinson dividers are used for power splitting and combining. In this work, we also use it for mode switching and signal routing. This allows one shared architecture to support multiple operating modes. This slide shows the switching concept. By controlling the digital signal, the circuit can operate in 3 modes. The first is high power PA mode. In this mode, both PA paths are turned on for power combining. The second is low power PA mode. Only one PA path is active. This enhances the efficiency at 6 dB backup operation. The third is low noise amplifier mode. The PA is turned off and the receive path becomes active. The mode selection is based on the switching behavior of the transistor. When the transistors are turned off, their parasitic capacitance from the pi-type network, which allow the RF signal to pass through. When the transistors are turned on, the path is shorted to ground, causing the LC network to present a high impedance which block the signal. This structure provides flexible operation with a simple control concept. Next is the LNA design, which uses a current reduced LNA structure. The main idea is sharing DC current between multiple stages. This improves power efficiency while maintaining high gain. This approach is useful for receive design because low power consumption is very important. Now let us look at the power amplifier. The PA supports two operation modes. In high power mode, both amplifiers have worked together to provide higher output power. In low power mode, only one path is active. This reduces power consumption. And this is practical because wireless transistors do not always need maximum output power. Next, I will show the result. This is my layout, and you can see the red area is the Wilkinson power divider gas switch, and the blue area is the low mode PA, and the pink area is the low noise amplifier, and the chip width is 850 micrometer, and the height is 900 micrometer. The results are divided in three parts: LNA mode, high power PA mode, and low power PA mode. So first, let us look at the LNA mode. The peak gain is about 22 dB at 50 GHz and achieve a 46% directional bandwidth. The input 1 dB compression point is around negative 20 dBm, which is acceptable for low noise amplifier operating in a CMOS fabrication. The minimum noise figure is about 7 dB. Although this is not an ultra low noise design, and we should remember that this is an integrated bidirectional front-end architecture. The DC power consumption is only 12 milliwatts, which is one strong point of this design. Overall, this LNA provides a good balance between gain, power, and integration. Now let us look at the high power PA mode. The peak gain is about 15.7 dB. The output 1 dB compression point is about 18.6 dBm. The separated output power is about 20.9 dBm. The peak PAE is about 25.6%. This result shows that the dual path power combining concept work effectively. Next is the low power PA mode. The peak gain is about 14.3 dB. The output 1 dB compression point is about 14 dBm. The peak power aided efficiency is about 14.5%. Compared with high power mode, output power combined become lower, but power consumption also decrease. This confirms that dynamic power scaling works as intended. This directly supports our original back of efficiency motivation. Now let us compare this work with previous study. Although this work does not optimize a single performance matrix to the absolute maximum, its key contribution lie in architectural integration and operational flexibility. We can see this work supports high power transmit mode and low power transmit mode and receive mode in one shared architecture. Also, the low noise amplifier only consumes 12 milliwatts, which is strong advantage. So the main value of this work is flexibility and system level integration. Conclusion. To conclude, we present 15 methods reconfigurable bidirectional front-end architecture. With configurable three-way Wilkinson network enables shared transmit and receive operation. And the dual mode PA support dynamic power scaling and 6 dB backup operation. Finally, the current used low noise amplifier provide high gain with low power consumption. And here is my reference. Thank you for your listening.
So, any questions? I would like to invite the 2 questions from the floor. Okay, so if no questions, I think you already provided quite comprehensive presentation regarding your research. And then your presentation starting with the problem positioning, right? And then go to the what? Try to point out the limitations of the existing work. If I'm not mistaken, you point out the 3 limitations. But for your motivation, you come up with the 4 target, right?
Yes.
So then the 4 target. So for the first one, try to simplify the complex circuit. And the second one, try to improve the PA efficiency. So based on the result you provided, I think I can see there's some improvement for the target 2. But for the target 3, enable the dynamic, the pizza high and low power operation. Is it because you utilize the one is what the free the LP, so LPA or HPA?
Yes.
Okay, that one.
Yes.
So would you please navigate to the page to show the mechanism to achieve the dynamic pizza high and low power operation? So should this one, right? So may I know how to achieve the isolation between these 3?
Yes. As I present, and I can show that if the transistor is shorted, when the transistor is on, and it's shorted in ground, and that the LC will become a oscillation tank, and this will provide a high impedance. That's the signal block.
Okay, got it.
Yes. And if the control is 0, and the transistor will become a capacitant. That is used for its parasitic capacitor. 就用它的寄生电容让它变成一个拍形保护。对。And let the signal pass through on our desired band. Yes.
Then how about the A1?
The A1 is the Wilkinson power divider resistor.
Yes.
So if we go through one pass, the resistor need to close. And we go through 2 pass, the resistor need to go on. This will provide the isolation between P2 and P3.
Okay, got it.
Yes.
Okay. Thank you.
Okay, thank you.
Yeah. So I would like to invite the next presenter, Wang Xiaoyu.
Today I will present our research titled Disturbance Resilient Energy Management Strategy for RPLG Vehicle Using Slightly Mode Observer Assist Auto Predictive Control. This work was supervised by Professor Jennington. Before we dive into the details, here is the outline of my presentation today. I will begin with a brief abstract of our work. use both role-based and model predictive control. Finally, I will discuss the core of our research, the sliding mode observer, and present the experimental result and conclusion. Now let's move on the upstream. The study focused on the battery and supercapacitor HESs. Traditional method often ignore converter advantages, which cause power gaps and speed drops. To solve this, we combine MPC with the sliding mode observer. The SNO estimated and compensated for the power losses in real time. This ensures precise speed tracking and optimal power speed, even under unknown disturbance. System architecture. First, look at the red block on the left, the power demand prediction module. We use an RBF neural network to analyze historical speed data and predict future speed. Based on this, we calculate the required power using the vehicle dynamic model. Next in the middle is the blue block, the MPC energy control module. It retrieves the power demand and calculate the optimal power speed between the battery and the supercapacitor. It then sends command to the converter controller to manage the power output. On the right, the yellow block is the drive system. The power provided by the battery and supercapacitor is used to drive the electric motor. However, in reality, there is a problem due to efficiency losses. The motor often receives less power than expected. To solve this, we use the green block, the SNO, to estimate this power loss. We add this estimate loss back to the demand. This allows the MPC to generate a compensating command, so the motor gets exactly what it needs. The vehicle dynamic model. First, we establish the vehicle dynamic model based on physical resistance. As shown in supercapacitor has enough energy. We enter mode 4. In this mode, we use the scaling factor data, making the supercapacitor contribute even more than in mode 3. Finally, if the supercapacitor SOC drops below the minimum limit, or if the power fluctuation is less than gamma, the system enters mode 5. In this case, the battery handles the demand and the supercapacitor only compensates this for any deficit. NTC. We upgrade from rows to optimization. The MPC use the predict horizon to look into the future. By using the speed predict by our RBF neural network, the MPC can do that the best power distribution for each time step. Its goal is to minimize cost function, which balance power demand, battery rotation, and supercapacitor stability. This allows the system to be much more proactive than the raw-based logic. To achieve this, we designed the cost function shown here. This consists of 3 key terms. First term, delta P battery. This penalizes rapid change by limiting fluctuation. We smooth the battery output and reduce internal thermal stress. Second term, P battery. This limits the peak power. This prevents high current stress, which is a major cause of battery degradation. Third term, SOC-SC. This focus on the supercapacitor. It forces the SOC to stay in the ideal range. This ensures it is always ready for acceleration or regenerative braking. Now let's compare the performance of RBC and MPC. Look at the power distribution chart. In the RBC result on the left, the battery power fluctuation perfectly to follow the demand. However, in the MPC result on the right, you can see the battery output is much smoother. This is because the MPC used its predictive horizon to shift the peaks, and that the supercapacitor handled the sudden change more intelligent. The numerical result confirm the superiority of MPC as shown in the table. The RMS current of the battery is reduced by 16.3% and the standard deviation is reduced by 25%. This reduction means less heat and lower electrical stress on the battery. By optimizing the power split, the MPC successfully extended the battery lifespan while maintaining system performance. Now we come to the core contribution of this study, the study mode observer. The observer estimates power loss, L of K, by defining a sliding surface, S of K, which is based on the error and the power gap and pass it back to the supply. Look at the configuration. The red and blue curve represent the standard method. They both suffer from speed drop because the actual power is less than required. However, look at the green curve. This is our proposed MPC with SMO. Check the reference speed almost perfect by active compensation. We successfully eliminated the power difference, reducing the speed error NAD by 56.5% and improving the stability by 7.9%. Beyond speed tracking, we also evaluated the system impact on battery health. To achieve high precision, the MPC with SMO slightly decrease the battery current to compensate for the power loss. However, this is a very efficient trade-off. Compared to the RBC baseline, our MPC with SMO reduced the battery RMS curve by 16.3% and extended deviation by 25%. This proves that our method not only track the speed accurately by eliminating the power difference, but also significantly protect the battery from high current strips. Conclusion. We successfully addressed the power deficiency and speed drop caused by converter inefficiency by integrating loss computation with predictive control. Our MPC with SMO framework achieves superior precision beyond standard MPC. Our main contribution include speed tracking improving precision by 56.5% on the dynamic cycle. Battery health, reducing RMS curve by 16.3% to mitigate stress. System robustness, building a high performance strategy that balances energy efficiency with operational reliability. Thank you for your attention.
Thank you for your presentation. Okay. One question from the
How did you set up your determinant test?
I use a random function to generate a power disturbance, which are mainly used to simulate the nonlinear and staunchest fluctuation of power loss caused by the converter in real-world conditions.
Where is the data source for the vehicle speed information?
The vehicle speed data is sourced from the UDDS, which is a standardized driving cycle defined by the U.S. Environmental Protection Agency. It represents typical urban driving condition in the U.S. characterized by frequent stop, low average speed, and moderate acceleration, making it widely used for evaluating vehicle fuel economy, emission, and energy management system performance.
Okay, thank you. I would like to invite the next presenter, Yan-Fu Xiang.
squeezing as a lightweight defense for adversarial robustness in hyperspectral image classification. My advisor is Professor Li Weihang, and I am Fu Xiangyan. The goal of this work is to evaluate whether visual squeezing can improve the robustness of HSI classification models under adversarial attacks while keeping the model architecture unchanged. This presentation is organized into 5 parts. I will first introduce the background of HSI classification and explain why robustness is important. Then I will describe the adversarial vulnerability of problem. After that, I will introduce visual squeezing as a proposed pre-processing defense. Next, I will present the experimental setup and results. Finally, I will summarize the findings and discuss future work. To begin with, hyperspectral images are different from RGB images. RGB images contain only 3 channels, while hyperspectral images contain many spectral bands for each pixel. Because of this, each pixel carries rich spectral information, and the whole image also contains spatial relationships between neighboring pixels. In HSI classification, the input is the whole HSI cube, and the output is a pixel-wise classification map. In this work, the accuracy is evaluated only on the test pixels. This pixel-wise classification ability makes HSI useful in many remote sensing applications, such as precision agriculture, environmental monitoring, urban planning, and disaster assessment. However, because the output is a full classification map, each pixel level prediction may affect downstream decisions. Therefore, if small input changes cause large classification errors, the reliability of the system becomes a serious issue. This motivates the need to study robustness in HSI classification. The main problem is that deep HSI classifiers can be vulnerable to adversarial perturbations. Even visually subtle noise may change the model prediction. The figure below is a simple RGB example used only to illustrate the attack mechanism. For HSI classification, this issue is more serious because the output is not just one label, but a full classification map. As a result, small perturbations may lead to errors across many pixels. To evaluate this vulnerability, I used FGSN as the attack method. FGSN generates adversarial examples using the gradient of the loss with respect to the input. This gradient indicates how the input should be changed to increase model error. The perturbation size is controlled by Ethel. In my implementation, I used a normalized gradient version of FGSN, where the gradient is normalized by the L infinity norm. The adversarial input is then flipped to keep it within the valid input range. After defining the attack, the next question is how to defend the model. There are 3 common defense directions. Robust architecture design can improve robustness, but it is usually model specific. Adversarial training is effective but increases training cost. Improved preprocessing keeps the model architecture unchanged, and my work focuses on improved preprocessing using feature squeezing. Feature squeezing reduces unnecessary input precision. For normalized HSI data, continuous input values are mapped into fewer discrete levels. This compresses the input space available to adversarial perturbations. In this work, I use quantization-based squeezing. The input is multiplied by label L, rounded and divided by L. The value of L controls the trade-off between preserving spectral details and suppressing small perturbations. Based on this idea, feature squeezing is inserted into both training and evaluation. During training, the clean HSI cube is first squeezed and then used to train the classifier. During evaluation, FGSN first generates an adversarial HSI cube, and feature squeezing is applied before classification. This SQ consistent design avoids distribution mismatch between training and evaluation. The model architecture itself is unchanged. Only the input representation is transformed. The hypothesis is based on the effect of quantization. Adversarial perturbations are small changes in continuous spectral values. After feature squeezing, these continuous values are mapped into discrete levels, so part of the perturbation's influence may be reduced. Also, because SQ is applied during both training and evaluation, the classifier can adapt to the squeeze input distribution. Therefore, SQ consistent preprocessing may improve robustness without changing the model architecture. To test this hypothesis, I use two defense settings: no defense and feature squeezing. I also evaluate two input settings: clean input and FGSN attack input. The experiments are conducted on 3 datasets and 3 models. The metric is overall accuracy, computed only on the test results. All reported results are averaged over 10 rows. I used 3 HSI datasets: R-value, Salinas, and EAP. They differ in scene type, spatial size, number of spectral bands, and number of classes. This allows the evaluation to cover both urban and agriculture or mixed land cover scenes. I evaluate 3 models. SSFCN is used as the baseline spectral spatial FCN model. SSENet uses self-attention context information for robustness. SSSNet further combines spatial and spectral self-attention. These models allow me to test whether SQ works across different classifier architecture. Before showing the results, I separate the evaluation into 2 settings. In the clean setting, no adversarial perturbation is added. This setting checks whether feature squeezing reduces the original clean accuracy. In the FGSN setting, the input is attacked by FGSN. This setting checks whether feature squeezing improves robustness under adversarial validation. First, I show the clean test results. The reported values are average OA over 10 runs, and the squeezing level is fixed at L equals 20. The goal is to check whether SQ hurts the original accuracy when there's no attack. Overall, the clean OA changes only slightly after applying feature squeezing. This suggests that SQ has limited negative impact on clean classification accuracy. Next, I show the FGSN attack results. Again, the values are average OA over 10 runs with L equals 20. Here, I compare FGSN without defense and FGSN with feature squeezing. Feature squeezing improves OA in all reported places. The improvement is more obvious for SSFCN, while SSENet and SSSNet show smaller but still positive gains. This suggests that feature squeezing improves robustness under FGSN attack. To further inspect the results, I compare the classification maps. This example uses Salinas with SSFCN. The four maps are ground truth, clean, FGSN, and FGSN plus SQ. For this case, OA drops from 94% in the clean setting to 54.94% under FGSN attack, and it improves to 73.82% after applying feature squeezing. Visually, the FGSN plus SQ map is more spatially consistent than the FGSN results. This supports the quantitative results. To conclude, this work evaluates feature squeezing as a lightweight preprocessing defense for HSI classification. In a clean setting, SQ with level 20 mostly preserves the original accuracy. In the FGSN setting, SQ improves the attack OA across the tested dataset and models. The improvement varies across models and datasets, but the overall trend is positive. For future work, I will test different squeezing levels, extend the attack setting to BGD, and evaluate more datasets or models. And here's my reference. Thank you for listening.
Okay, thank you for your presentation. I would like to open the floor for the questions. Any questions?
Why did you choose the squeezing level L equals to 20?
At this stage, L equals 20 is used as an initial fixed setting to evaluate whether SQ has potential. It provides a moderate quantization strength, not too aggressive, but still able to reduce small perturbations. The reported results are average over 10 rounds to reduce randomness. However, L equals 20 is not necessarily the optimal value. The next step is to test different different squeezing levels and analyze the trade-off between clean accuracy and robustness.
So your experiment currently uses only FGSM. So can we say the feature squeezing is attack agnostic?
I would say the method design is attack independent, but the current experiment only verifies the under FGSM. Feature squeezing does not use the internal formulation of FGSM. It only transforms the input before classification. So in principle, it can be applied to inputs generated by different attacks. However, experimentally, I should not claim for attack agnostic robustness yet. Thus, to support that claim, I need to evaluate stronger attacks such as PGD and possibly adaptive attacks that know the SQ operation. So the current result should be interpreted as an initial evaluation on the FGSM.
Why you don't use a lesser version instead of feature squeeze?
Thank you for the question. We choose feature squeezing over advanced version for three main reasons. The first is zero training overhead. It doesn't require days of computational power to generate adversarial samples during training. The second is architecture agnostic. It is a plug and play preprocessing step. It can be applied directly to any existing HSI classification model without architectural changes. The last is preservation of clean accuracy. As shown in our experimental results on slide 8, feature squeezing maintain sometimes even slightly in improvement classification accuracy on clean data, avoiding the typical performance trade-off seen in adversarial training.
Okay, thank you. Thank you. May I ask last presenter of the day, Wang Chen An?
Hello everyone, my name is Wang Chen and my advisor is Professor Guo Tianhong. Topic of my presentation today is the second order result based continuous time delta schema modulator with PI protocol. And here is the outline of my presentation today. First, I will go through the introduction and limitation to discuss the background of this research. Then I will provide a brief overview of delta sigma modulator to look at the traditional design and their limitation. Move on, I will present the proposed architecture and dive into the detailed circuit implementation. I will show the simulation result and conclusion. The real world we live in entirely analog, such as human hearing and environment sensing signal. However, modern IT systems really on digital critical signal for high performance storage and advanced DSP operation. To bridge these two distinct worlds, mixed signal circuit serve as a critical backbone. For example, when a microphone captures an analog voice signal, it undergoes amplification and filtering and must pass through the core of this research. Analog to digital converter. By converting the waveform into digital bit, the backend digital system can finally perform high-level processing like voice recognition. In the entire sensing front-end, the ADC's performance directly determine the signal fidelity and precision, driven by the extreme constraint of modern IoT application. So, how to design an ADC that achieves both high fidelity and ultra-low power consumption under a low supply voltage is the core motivation of this research. Then, why did this research select the delta sigma modulator as our application? This decision is primarily based on two critical design advantages. First, oversampling technology. Since our target voice application operates in the low frequency audio range, oversampling allows us to significantly lower the in-band noise floor. And the second, the most importantly, noise shaping. Through the loop filter, the system aggressively push the in-band combination noise away to higher frequencies. By combining these two technologies, we can utilize a very simple low-bit compiler to achieve a higher dynamic range and resolution. This makes delta sigma the perfect candidate for our low power and high resolution requirement. After the modification, we will move on to the second part, the overview of delta sigma modulator. In this table and block diagram, compare continuous time and decrease time architecture. Decrease time delta sigma are immune to clock jitter and other precise coefficient. However, their switch capacitor input stage generated severe switch noise. In contrast, continuous time delta sigma offer relaxed amplified speed and a simplified sampling circuit and low switch noise. So higher than the bottom, thinking ultra low power for IoT audio, this works like continuous time delta sigma to eliminate power hungry front-end buffer by leveraging this implicant anti-aliasing nature. Next, let's look at the circuit level implementation for the first stage integrator. And GNC integrator offer a high speed and a low power consumption, but its linear is poor because it heavily depends on the transconductor transistor characteristics. Under a low supply voltage, large signal swing will have severe harmonic distortion. So to overcome this linearity bottleneck, this will adopt the active RC integrator for our first stage. By utilizing the operational amplifier, active RC establishes a highly stable virtual ground. This guarantees an excellent linear relationship between the input voltage and current, achieving a high linearity and a wide dynamic range, and strong robustness against parasitic. Although it consumes more power consumption, but it's a trade-off essential to maintain high performance in our research. As I mentioned on the previous slide, although the active RC for the first stage guarantee an excellent linearity, conventional second-order architecture faces the challenge of high power consumption.
So to solve this analog power bottleneck, recent research has driven the architecture evolution shown in this diagram. Moving from the early flash ADC to the later ADC architecture, which successfully save power at the quantizer stage. The system still could not escape the hardware overhead of required two active op-amp. Consequently, recent research has shifted toward the VCO-based architecture. By leveraging the physical property of the VCO, where is the output phase continuously documented in the time domain and inherently providing infinity DC gain, we can directly replace the second stage analog integrator. This successfully streamlined the loop to require only single active op-amp while reducing the power consumption. It also provides a perfect foundation for our proposed automation architecture, and I will introduce next. When we enter the third part of the presentation, the proposed architecture. This slide demonstrates how we break through the traditional design bottleneck by eliminating the secondary feedback path. In the figure A, which shows the conventional architecture in a traditional second-order continuous time modulator, and independent secondary feedback path is typically required to guarantee a closed-loop system stability. However, this extra path introduces significant side effects. It not only increase analog thermal noise, but also consume more power consumption and achieve area. So to overcome this critical pain point, I propose the upper-dimension architecture shown in the figure B. We completely remove the secondary feedback path. To mention system stability without Jack 2, we upgrade the first stage integrator in a proportional integrator network. This design delivers substantial system benefit. First, it successfully creates the required stability zero without introducing any extra second deck hardware. Second, it streamlines the entire modulator to utilize only a single feedback path. This major breakthrough in hardware simplification is precisely the key to achieve extreme energy efficiency in this research. After the proposed architecture, we will move on to circuit implementation. First, before diving into a detailed circuit implementation, we establish the system specification table right at the beginning of our design process. This ensures that we fully meet our target for both low power and high resolution. And after establishing the specifications, we must perform precise behavior model of the system. To implement our proposed architecture, we first derive the continuous time open loop transfer function. Then, to accurately account of the impact of extra loop delay on stability during transistor level implementation, we use the impulse invariant transformation. This allows us to incorporate the nonlinear delay into our calculation and deriving the Z domain and its corresponding system coefficient E1, D2, and D3. And finally, use the NTF and STF. We import this precise mathematical model in MATLAB to perform loop coefficient. And this slide presents the ideal performance result of our behavior level simulation conducted in MATLAB. As shown in the power spectrum testing, ideal peak SNDR to reach are 101.17 decibel, which corresponds to an ENOB of 16.51 bits. This providing strong the theoretical support for the feasibility of our proposed architecture. And finally, to ensure the system will not suffer from oscillation during actual operation, we analyze the Lucas probe on the top right to verify system stability. As illustrated in the part, all closed loop poles of the system are perfectly located with the unit circle, and the maximum magnitude is only 0.758. This confirms that the set of circuit coefficients we derive provide the system with a high robust stability margin. This slide presents the actual transistor level circuit implementation of our proposed chip. First, in the front-end proportional integrator network, the active amplifier is realized using a 40 Pascal op-amp and a common mode feedback circuit to provide high DC gain and stable output common mode voltage. And next, integrated signal into the differential ring VCO for time domain integration. For the underlying DSL, we adopt the dual cross-coupled cell DSL to guarantee excellent differential symmetry and linearity. After the VCO stage, the output phase are quantized into a 16-bit digital output by the phase quantizer, which is composed of sense amplifier and exclusive OR gate. Finally, to maintain a high energy efficiency and operating speed for the entire system, the feedback pad utilizes the fully differential curve steering deck to implement the non-return to zero deck. And finally, let's look at the simulation results. The circuit was designed in a 180 nanometer CMOS process with a 1.8 volt analog and 1.0 volt digital supply, operating at a sampling frequency of 2.56 megahertz and signal bandwidth of 20 kilohertz. We apply a 5.93 kilohertz sine wave input. The simulation achieved a peak SNDR of 87.3 decibel. The total power consumption is only 185 megawatts. This translates to excellent F1S of 167.6 decibel and F1W of 214.5.7 femtojoule per convolution step. And this is my conclusion. So by introducing the proposed proportional integrator network, we have successfully eliminated the secondary feedback. This change creates the required stability zero without sacrificing system stability, while streaming the loop to utilize only a single active amplifier and a single feedback pad. The verified performance clear prove that our achievement hold great potential for ultra-low power voice IoT application, delivering both high resolution and extreme energy efficiency. Thank you for your attention.
Thank you. So, any questions from the floor? any questions to our last presenter? Okay. I have a question for you. Would you please name a few like a trade-off of using the one active op-amp plus VCO?
就是如果我用 VCO 的话，你最容易受到就是 VCO 非线性的影响，所以说我要靠着我自己的计分器，我去把它的可能loop gain 提高，然后这样子它就显示出。
And then, what else? Okay, so now if the op-amp, the gain of the op-amp is insufficient, not big enough, and also like the bandwidth is not enough. So what happened to your modulation?
从频谱就可以看到，就是你的三度频失真就会很严重，
对，
它就不会是一个干净的频谱。对。
Oh, okay. Any questions? Okay, if no question, thank you. Okay, so about time to close today's session, and then see you next week. Bye bye.